to be heading. But before going into that specific application, there's just a little bit of theory of Markov matrices we have to look at. It's nothing too bad. So there's, I think, 2 homework problems on the homework next week that has to do with Markov matrices, but they should go pretty quickly, as you'll see. A lot of this just comes down to finding an eigenvector, just like a single eigenvector. It's called the steady state vector. So that's what's going to be relevant. Okay, so what are Markov matrices? An n by n matrix is going to be called a Markov matrix if all the entries are going to be non-negative. Actually, yeah, so all the entries are non-negative, and then the sum of each column is going to be equal to 1. So you should be thinking of the columns of your matrix as being sort of like a probability vector, right? That's what it means, like they're all non-negative. So like all probabilities are going to be non-negative. And then for the sum to be equal to 1, it's saying that like all the probabilities end up adding to 1. So every possibility is represented. So that's the next statement. Like you should interpret the columns as being a probability an event is going to occur. And so we're going to be looking into various applications of Markov matrices. And these are one of the most important aspects or applications of linear algebra. And people are interested in probability in general, like being able to predict what's going to happen in the future based off of previous data. And you usually want to be using Markov matrices to determine this, like, or predict future information. So there's 2 propositions we need to prove before we move on to the main ideas of this section. The first is going to give us, or it's going to tell us that Markov matrices are closed under multiplication. So if A and B are Markov matrices, then A times B is going to be a Markov matrix. And then the second proposition, which is actually the more important of the 2, I would say, is going to give us some detail about what the eigenvalues look like, as well as, well, how it relates to other eigenvalues. Okay. So this is going to be the important proposition. The fact that we have lambda is equal to 1 always for Markov matrices is going to be very important later on. Okay, so the first proposition, I'm not going to go into like what's like an n by n matrix, like what's the matrix formula end up looking like. Let's just look at 2 by 2 matrices and see what happens. This isn't really like the important part of the lecture. So let's just look at what happens for 2 by 2 matrices. So if we look at 2 by 2 matrices, say we have 2 Markov matrices, just A, B, C, and D. And then we have another Markov matrix given by E, F, G, and H. Maybe you can be more creative in your labeling than me. So these are 2 Markov matrices. So if we want to show that these 2 matrices are closed under multiplication, you just multiply them together, and then you see if the columns end up adding to 1, right? I mean, all these entries are non-negative, so if you take the product of the 2, the entries will still be non-negative. So if you do, let's maintain the blue. So this is A, B, C, and D, multiplied by E, F, G, and H. If you take the product of these 2 matrices, you get AE plus BG as the first entry, and then you get AF plus BH as the 1-2 entry. You get CE plus DG in the 2-1 entry, and then you get CF plus DH for the 2-2 entry. Okay, so what matters here is we just need to make sure that these 2 columns end up adding into 1 like this. The sum of these 2 entries have to add into 1. The sum of these 2 entries have to end up adding to 1 as well. And so if we just look at the first column, pretty much the same idea will hold for the second column as well. So if we do AE plus BG, and then we add to that CE plus DG, well, this is going to be equal. So what do we already know? We know this is a Markov matrix. We know this is a Markov matrix. So we know A plus C is going to be equal to 1. We know these, like B plus D is equal to 1, E plus G is equal to 1, F plus H is equal to 1. And so we have like an AE plus a CE. So we'll have like an A plus C if we factor out the E. So this is really equal, just rewriting the sum. This is really AE plus CE, and then plus BG plus DG. And so this is, you can factor out the E to get that this is going to be E times A plus C, and then plus G times B plus D. Again, A plus C is equal to 1. B plus D is equal to 1. So this is equal to just E plus G. And then we have that E plus G is equal to 1 as well. So this is equal to 1. Right, so we've showed that if we multiply these two matrices and then look at the resulting column, if you take the sum of the entries of that column, you still end up getting 1. And then the same argument holds for this sum as well. Like nothing really changes. So you can add these two numbers, except now you'll factor out an F. So you get A plus C multiplied by F, which would just be F, and then you get B plus D times H. So you factor out the H. So it's the exact same idea over again. You can generalize this to any n by n Markov matrix, but that's not really the interesting part of today's lecture. Okay, any questions about this proposition? Okay, so that's verifying that the product of two Markov matrices is going to be another Markov matrix. This proposition will be used in this very next proposition. The next proposition tells us that if A is a Markov matrix, then A is going to have lambda is equal to 1 as an eigenvalue. And then more important, well, maybe not more importantly, just as importantly, we have lambda is equal to 1 is going to be larger than any other eigenvalue. So lambda is equal to 1 is an eigenvalue, and it also happens to be the largest eigenvalue. And this is going to be like a really influential statement in today's theory, or the theory of today's lecture. So let's just break it in two. Again, I'm going to be pretty informal in going about the proofs of these statements. I don't want it to be like a super proof-based lecture today. So the first statement we'll prove that lambda equals 1 is an eigenvalue. So lambda equals 1 is an eigenvalue. It's the first statement we'll show. And again, we're going to want to make use of the fact that the columns of A end up summing to 1. So the columns, just like we'll put together a couple of observations pretty much. So the columns of A sum to 1. And so if we want to show that lambda is equal to 1 is an eigenvalue, we should be thinking about what happens if we end up subtracting 1 from an entry of our column, right? Like if we're determining if lambda is equal to 1 is equal, or lambda is equal to 1 is an eigenvalue, like you take your matrix and you subtract 1 along the diagonal. And so what this is really saying, or how we can utilize this information, is if we just write the same statement over again, except we do A minus 1, we have like the columns of A minus the identity are going to sum to 0. Just as a quick example, like demonstrating this, and maybe it's clear already, but if you have a Markov matrix like 0.4, 0.6, 0.3, 0.7, if you were to subtract 1, let's do a little bit more space here. If you were to subtract 1 by the diagonal, so the sum of these entries, or this column is 1, sum of this entry or column is 1. If you were to subtract 1 along the diagonal, you would end up getting minus 0.6, 0.3, and then 0.6 minus 0.3, right? So now if you took the sum of the column entries, you would end up just getting 0. So that's what I'm saying here, right? We had a matrix A, the columns sum to 1, and then if you subtract 1 from the diagonal, the columns sum to 0. And so what does this mean? This is really telling us that the sum of the rows is going to be the 0 row. So the sum of rows is going to be the 0 vector. I should be a little bit more specific. The sum of the rows of A minus the identity. Right. Like if you took the sum of these two rows, you just get 0, 0. That should be pretty clear. Okay, so if we have that the sum of the rows, I'm gonna ask you, maybe you have the answer. If we take the sum, if we have a matrix and we take the sum of the rows and they end up being equal to 0, what does that say about our matrix in terms of like how are the rows related to one another? Like are you going, I don't want to use the two words. I was gonna say like are they blank or are they blank? If I use those words, it gives it away. What can we say about the rows and how they relate to one another? Yeah. Yeah, that's what I'm looking for. So this means that the rows are dependent. So the rows of A minus lambda are dependent to one another. And so if we know that the rows of A minus I are dependent, what does this say about the determinant of the matrix? Oh, I'm asking you. So if we have like dependent rows and we take the determinant of that matrix, what does the determinant end up being? 0. Yeah, it just ends up being equal to 0. This is like one of the determinant rules that we know, right? And so if we have this determinant of A minus I is equal to 0, I mean, this is what we do to show that we have an eigenvalue, right? Like we take a matrix, we subtract lambda by the identity, we set it equal to 0 and find the solutions. So this is saying that lambda is equal to 1 is an eigenvalue, right? So this implies that lambda is equal to 1 is an eigenvalue. Which is exactly what we wanted to show, right? We wanted to show lambda is equal to 1, it's an eigenvalue, and we've done that. And we didn't have to do anything too fancy, just using the fact that the columns end up summing to 1. So if you subtract 1 from one of the entries, it ends up summing to 0, which then means the rows are dependent, and then lambda is equal to 1 will be an eigenvalue. Okay, any questions about this part of the proof? Okay, the other statement, I'm just going to kind of lean on intuition without going into too much detail. So the other statement is lambda is equal to 1 is the largest eigenvalue. And so the main idea to show that lambda is equal to 1 or understand that lambda is equal to 1 is the largest eigenvalue is we use the fact that the product of Markov matrices are going to, again, be a Markov matrix, right? So what we know is for any k greater than 0, we have that A to the kth power is a Markov matrix. And so the idea is, again, I'm not going to go, I'm like leaning on the intuition without going into too much detail. And maybe this is like a little flimsy and you can like back this up with more detail. But the idea is if we're always having that A to the kth power is a Markov matrix, this means the columns are always going to be summing to 1. So in a sense, like, are this matrix A, like it's never really growing, even though we're applying all of these powers. You would expect it to grow, but it's kind of like staying the same in a sense. So if we had, so this is like the first observation. The other observation is if we had some lambda such that lambda was strictly greater than 1, this would imply that A to the kth power would be growing. To infinity. The reasoning behind this, again, there's a relationship between the power of a matrix and the eigenvalues and eigenvectors. Like you can write any matrix or a vector as like a sum, like a linear combination of the eigenvalues and the eigenvectors. So if you have lambda greater than 1 and you take a bunch of powers, it means your matrix will blow up to infinity, or this matrix power would blow up to infinity. So this is going to imply that we have to have that the eigenvalue or the eigenvalues are going to be less than or equal to 1. And again, there's more detail you can go into, but this is the major idea. I don't want to get bogged down in writing like a page of proofs or anything like that. Okay, so this is the idea behind like the proof of this proposition. Again, we are using the fact that the product of Markov matrices is, again, going to be a Markov matrix here. Okay, any questions before moving on? Okay, so the next page is the important part. Like these are just two propositions we'll make use of today. But this next page really goes into, or next page and a half really goes into why Markov matrices are important or how they can be utilized. Okay, so I guess like the question to frame this is like, why do we care that Markov matrices are again Markov? And why do we care that they have a maximum eigenvalue of 1? So we'll just look at a sample Markov matrix. I'm not going to put any like context around this. We're just given a Markov matrix, and then we'll look at a more interesting context later on. And so you can see the columns add to 1, and each of the entries are non-negative. And so we think we're going to look at what happens if you multiply A by some positive vector. So this is just going to be 0.5, 0.5. There isn't anything special about this vector. I just chose a random Markov vector, so you can see these two entries sum to 1. But they don't have to necessarily sum to 1. Actually, they should sum to 1 to make sure that the multiplications actually end up being Markov matrices again. But you could have done like 0.2, 0.8, 0.3, 0.7, or really any two entries that sum to 1. And so what ends up happening to this vector? So this is our original vector. If we multiply by A, we'll get a new vector denoted by U1. This is going to end up being 0.55, 0.45. And then we're just going to keep on multiplying this vector by A, potentially like infinitely many times. Like we'll take a limit eventually. And so U2 corresponds to doing A squared times U naught, this initial vector. U3 corresponds to multiplying U naught by A cubed. And you can see with these various multiplications of A that we're doing on our vector, the resulting vector is going to converge. Like it's getting closer and closer to converging to a specific vector. That vector being like, it seems to be converging to 0.6 and 0.4. And so after k steps, we have, this is just general notation. UK is equal to a to the k power times this initial vector U naught. And you can see that the vectors U1 or U naught, U1, U2, as k goes to infinity, it's approaching what's called a steady state vector. And so the steady state vector is going to be denoted by U infinity. And you can see it's equal to this vector 0.6, 0.4. Again, I'm doing this in a pretty informal way right now, but we'll make it more rigorous later on, right? Like you'd actually have to show, like you'll find a formula for these vectors and let k go to infinity. And then you'll be able to confirm rigorously that U infinity, the steady state vector, ends up being equal to 0.6, 0.4. And so as I was saying before, this outcome doesn't depend on the starting vector. It doesn't matter that we started with 0.55. If you started with 0.2, 0.8, or 0.7, 0.3, it would still end up converging to the exact same steady state vector. Again, it's completely invariant on U naught, this initial choice. So as long as U naught is a Markov vector, say if A plus 1 minus A would be equal to 1, we end up converging to the same U infinity or steady state vector. And so this is going to be giving us important information. Really, the main takeaway from this is the following. So the steady state vector, a natural question to be, would be like, what if we just had the initial condition was just equal to the steady state vector? What would end up happening? This will give us useful information, and that if you do A times the steady state vector, so this is our matrix A multiplied by the vector that these vectors end up converging to. Again, because this is the steady state vector, you end up just getting 0.6, 0.4 again. Like it ends up fixing this vector via multiplication. So it doesn't change anything. And so in terms of eigenvalues and eigenvectors, what we have is we have A times U infinity is just equal to U infinity, which is saying that U infinity is going to be the eigenvector of 1, right? So U infinity is an eigenvector with eigenvalue 1. Right, and so we were already saying in the previous page that like these Markov matrices, they always have an eigenvalue of 1, and 1 happens to be the largest eigenvalue as well. And now we know that the eigenvector is this steady state vector. It has this particularly nice property where like the powers of A multiplied by a Markov vector ends up converging to this eigenvector. And so the question is like, why do these powers of A multiplied by some vector, like why does it end up converging to the steady state vector? So that's what we're going to be looking at next, or answering next. And so the key point, again, is just going to be relating powers of A. with eigenvalues and eigenvectors. I was like framing things in terms of diagonalization, but we aren't really using diagonalization here, or at least explicitly. Like we are using diagonalization in a sense, but I'm not writing it out in the way we typically use or write out diagonalization. And so if you look at this matrix, going down to this second paragraph here, if you look at this matrix A, we know one of the eigenvalues is going to be 1. To determine what the other eigenvalue is, you use the fact that the trace of a matrix is equal to the sum of the eigenvalues. So we have the trace of this matrix is 0.8 plus 0.7, so the trace is 1.5. As one of the eigenvalues is equal to 1, the other eigenvalue has to be equal to 0.5. So we have these two eigenvalues, 1 and 0.5. And then I just tell you what the corresponding eigenvalue vectors are. So we know one of the eigenvectors is v1, which is 0.6.4. And then it turns out the other eigenvector is going to be -1, 1. This corresponds to lambda is equal to 0.5. And so to understand why this matrix powers converge to the steady state vector, what we're going to do is we're going to take this initial vector 0.5, 0.5, and we're going to write it as a linear combination of the eigenvectors that we have. So you can write 0.5, 0.5 in the following way. So 0.5, 0.5 is really just equal to 0.6.4. And so we want to go from 0.6 to 0.5, and then we have like a minus 0.1. So this is going to be plus 1/10 multiplied by -1, 1. You can see this ends up working, right? If you do 0.6 plus -1/10, you would get 0.5. And then 0.4 plus 1/10 would give you 0.5, right? So this is how you can express this vector u naught in terms of this linear combination of eigenvectors. And now we want to think what happens if we multiply A or multiply u naught by A in terms of this linear combination, using the fact that these are eigenvectors with specific eigenvalues. So I kind of wanted you to figure this next part out on your own, but I kind of also want to finish this out, like this lecture out in one class. So I don't know. I feel like you should try and let's work through this. Try figuring out this example actually on your own, maybe for just like 5 minutes, see what you can do. So this is like the key idea. So we want to determine a formula for UK, where UK is AK times this 0.55 vector as a linear combination of eigenvectors, v1 and v2. Wants you to take the limit as k goes to infinity to find the steady state vector. And then it wants you to determine why does u infinity equal the eigenvector of lambda is equal to 1. It sounds like a lot, but it really just follows from one observation. So think about it for a couple of minutes and see where it takes you. So it probably wasn't enough time, but I want to make sure we're moving ahead here. So this is our initial vector. U naught is this 0.5, 0.5. And we're writing it as the sum of these two eigenvectors, where this is an eigenvector with eigenvalue 1, and this is an eigenvector with eigenvalue 0.5. And so we want to look at the various powers of A and how they influence or how they change this U naught. So we have U1. This is equal to A times U naught. You can write this as being equal to A multiplied by 0.64 times 0.4 plus 0.1 multiplied by A multiplied by minus 1, 1. Right, all I did was, if we're multiplying A by U naught, you can distribute the multiplication of A throughout this sum. So that's what I did going from here to here. And then we want to use the fact that this is an eigenvector with eigenvalue 1. With this in mind, this is going to be equal to 0.6, 0.4. Maybe let's write it like this, actually. I don't know if it's clear why I'm doing this. So this is equal to 1 multiplied by 0.6, 0.4. Due to the fact that 0.6, 0.4 is an eigenvector with eigenvalue 1. This will be plus 0.1 multiplied by, so this is an eigenvector, minus 1, 1 is an eigenvector with eigenvalue 0.5. So this A times this eigenvector is really just 0.5 multiplied by minus 1, 1. And then we can think what ends up happening when we multiply U1 by A. So that would just be multiplying this whole thing by A again. So we have U2 is going to be equal to A times U1. This will be equal to A multiplied by 0.6, 0.4 plus 0.1 times 0.5 times A times minus 1, 1. You can then write this again as just 0.64, 0.6, 0.4 plus 0.1, 0.5. And again, we're using the fact that minus 1, 1 is an eigenvector of A with eigenvalue 0.5. So you're going to get 0.5 squared multiplied by minus 1, 1. And now you can kind of see what's going to end up happening, right? So if you generalize, we're going to have that U, K. This is equal to A to the kth power multiplied by U naught. This is going to end up being equal. So even though we're multiplying U naught by A, it doesn't change this 0.64. Like the 0.64 stays the same because it has an eigenvalue of 1. So this is going to be equal to 0.6, 0.4. Then this will be plus 0.1. And then with every multiplication of A on this eigenvector minus 1, 1, we're going to be multiplying that vector by 0.5, like the eigenvalue 0.5, right? So if we did like A squared, we got 0.5 squared. So if we're doing A to the kth power, this is going to be 0.5 to the kth power multiplied by minus 1, 1. And so with this in mind, if we let the limit or consider the limit as k goes to infinity of uk, this is equal to the limit as k goes to infinity of A to the kth power times U naught. This is really going to be equal. So this is the limit of what I have written above. This is a limit of 0.6, 0.4 plus 0.1 times 0.5k minus 1, 1. And so the idea is the only time the k shows up is it's this power of the eigenvalue of an eigenvalue that's less than 1. So as k goes to infinity, this whole term is going to go to 0. And so you're just going to be left with 0.6, 0.4, which is the eigenvector, again, of lambda is equal to 1. And so this is the main idea behind what's happening. Like it's really important. The main idea, like most important idea, is the fact that with these Markov matrices, you always have an eigenvalue of 1, and it also happens to be the maximal eigenvalue. So that if you write a vector as a linear combination of these eigenvectors, the only eigenvector that will remain if you take enough powers is just going to be the eigenvector corresponding to 1. So that's why this vector UK ends up converging to the eigenvector that corresponds to lambda is equal to 1. And all the other eigenvectors go to 0 over time. Okay, any questions about this idea or this example? Okay, and so this is the main theorem of this content. So the result from the previous example generalizes for any Markov matrix A, assuming that A has positive entries. So we found that if A is a positive Markov matrix, so the entries are all going to be positive and each column adds to 1. Then we have that lambda is equal to 1 is the largest eigenvalue. And then the eigenvector x1 is the steady state. Right, and so we always have the following decomposition. So this is what we showed in the previous example, but it generalizes to n by n positive Markov matrices. So you can always write UK as some linear combination of eigenvectors. So x1 is the eigenvector corresponding to lambda 1. Then you have these other eigenvectors. And as k goes to infinity, as these lambdas are less than 1, they end up going to 0. So this UK converges to just x1 upon taking the limit. So this is what we demonstrated for this specific example above. Okay, so this is going to be very useful in being able to predict future behavior, or really like probabilities in general. Okay, so the main application today is we're going to be looking at Google's PageRank algorithm using these steady state vectors and Markov chains. So I guess the pitch is that internet searching in the 1990s was very inefficient. Like, I guess like the top dogs back in the day were Yahoo or Alta Vista. I don't even know what this is. But like how they used to do like searches would be like if you put in a text into the search engine, they would pull up the web page based off of how many times the text would show up on that web page, not in terms of like how important that web page is, in terms of like how many other web pages linked to that website. And so there are two guys, I don't know if they're like CEOs of Google or what, but they're very rich. So there's like Larry Page and Sergey Brin, I don't know how you pronounce his name, came up with a new way of thinking about rank pages by importance or ranking pages by importance. And they use like these Markov matrices and eigenvalues and eigenvectors to determine importance. So they founded Google based on their algorithm. And so this is going to be a very, I guess, super like surface level explanation in terms of how it works for like really small examples. Like the matrices they're looking at are like, they have like trillions of rows and stuff like that. Obviously, we're not going to be doing that. We're looking at rows, like a matrix that's like 4 by 4. And so how this works is each web page is going to have an associated importance, which is going to be denoted by rank, which is going to be a positive number. And so the rank is going to be determined by the following rule. It's known as the importance rule. So if you have a page P that ends up linking to n other pages denoted by Q1, Q2 up until Qn, then we're going to say that each page Qi in this list is going to inherit 1 over n of P's importance. And so from this importance rule, we can come up with an importance matrix. So we're going to consider an internet with n pages. The importance matrix is going to be an n by n matrix whose ijth entry is going to be importance that, or the importance that page j passes to page I. And again, I think it just helps to see like someone write out an example to understand how to create these importance matrices. So we're going to consider the following example. We're going to consider the following internet that only has 4 pages. The pages are A, B, C, and D. And then the links from one page to another are denoted by these arrows. So we have A links to B, and A links to D, as well as C as well. And then you can follow the same logic for these other matrices. And so it wants us to determine what the importance matrix is going to end up being. And so I think it would be helpful to just label each of these arrows to determine what the importance of one page to another page is going to be. So if we're just looking at A, and we're thinking about like what's the importance of A to B, C, and D. Well, A links to 3 other web pages, B, C, and D, So the list, like these QIs, like Q1, Q2, Qn, like n in this case is going to be equal to 3. And so each of these web pages, A, B, or each of these web pages, B, C, and D, will inherit 1/3 of A's importance. So this is going to be like 1/3, 1/3, 1/3. And so the first column of the importance matrix is going to be 0, 1/3, 1/3, 1/3. So you should be thinking like we're starting at like A, B, C, and D. And we're going to A, B, C, and D, right? So there's a 0% chance A goes to A because it doesn't have a loop. There's a 1/3 chance that A goes to B, 1/3 chance that A goes to C, 1/3 chance that A goes to D. And then you can do this for all the other pages as well. So now thinking about where does B go? B goes to 2 web pages, it goes to C, and it goes to D. So this is going to be 1/2, 1/2. So B doesn't go to A, so this is going to be 0, 0, and then 1/2, 1/2. C doesn't have, C only goes to A. It only has 1 link. So this is just going to be a 1. All the other entries will be 0. And then we see that D goes to A and it goes to C. So those arrows have an importance of 1/2. So this will be 1/2, 0, 1/2, 0. So the idea should be pretty intuitive. Right, you just like see which web page goes to which web page, and you assign a probability of going from one web page to the other web page, and then you end up getting the following matrix. Okay, any questions about finding the importance matrix? Okay, so hopefully that's pretty clear. What's unfortunate about the importance matrix is if you look at the matrix, there's plenty of entries that are not going to be positive. And for this main theorem to work, this theorem from the previous page to work, it only applies when we have that A is a positive Markov matrix. So each of the entries have to be strictly greater than 0. So this theorem doesn't apply to this importance matrix. So we have to do a workaround on this thing. And I guess it's worth mentioning too, this importance matrix will always be a Markov matrix, right? I didn't say that, but hopefully you noted that this is a Markov matrix, right? The columns all sum to 1. And so this is how Page and Breen worked around the fact that the entries weren't always going to be positive. So the first thing they did is they made it so if you have an importance matrix where you have a web page that doesn't go to any other web page, i.e. you have a column of zeros, you replace your importance matrix A with another matrix, A prime, where instead of having this column of 0, you replace each 0 column with a column of 1/n, where we have that n is the number of pages that we have. So here we have a 3x3 matrix, so we have 3 different pages, and we have a column of 0. So we replace A with A prime, where this column of zeros is replaced by 1/3, 1/3, 1/3. So this ensures that it's still going to be a Markov matrix. And so this still isn't like all positive entries though, obviously. Like we still have 0, 0, 0, 0 here. So we need to do some further work to determine another positive Markov matrix that will get rid of these zeros. And so what they did is they're going to modify this A prime again. So we're going to take a number P from 0 to 1. So this is really just a probability called the damping factor. And a typical value is apparently this P is equal to 0.15. So this is like a 15%. And so what they did is they created what's now known as the Google matrix. And so if you have that A is the importance matrix for an internet with n pages, and we let A prime be the modified importance matrix, we end up having the following matrix, which is called the Google matrix. And so it's defined in the following way. We define M to be 1 minus our damping factor multiplied by A prime, where A prime is just A, where you replace the 0 columns with the 1/n's. And then we add to this a matrix P multiplied by B, where we have like P, or we have B is this completely random matrix. Like it's just a matrix consisting of all ones divided by n. And this, I didn't really type this up very well. It looks kind of weird, but right. I guess maybe there should be like a final column of ones at the end. I kind of wrote out the matrix in a weird way. Okay, so this is what's known as the Google matrix. And so what's going on with the Google matrix? This is something you can talk a lot about, but I don't have that much time. So I'll just give you like a basic interpretation. So the idea is with a probability P, the surfer will surf to a completely random page. So what this means is if our probability, like there's a probability P that the surfer will go and choose a completely random page, that's this guy right here. Like this matrix B, you should be thinking in terms of like, this is completely random, right? It's just like 1 over n, 1 over n, 1 over n. Like there isn't any favorability going from one page to another web page. Otherwise, they click a random link on the current page, which is represented by this 1 minus P multiplied by A prime. If the page doesn't have a link, and then they end up just surfing to a completely random page in either case. And so I'm not going to go through this next example, but it turns out the Google matrix is a positive Markov matrix. You can just do it for 3 by 3 matrices to see generally what ends up happening. But it ends up being like all the entries are going to be strictly greater than 0, and the columns end up adding to 1. So I'm going to skip this part, the example. But like the theory ends up working when you make this adjustment is the big idea. Okay, and so what do we do with the Google matrix? Like, why does the Google matrix matter? In a sense, it's going to be telling you like the importance of the web pages that you have. At least if you look at the eigenvectors. So like there's a particular eigenvector that's going to give us worthwhile information from this Google page or this Google matrix. And I guess it's now called like a $25 billion eigenvector. So we're going to be looking at what's called the PageRank vector. This PageRank vector in mathematical terms is going to be the steady state vector of the Google matrix. And from what we were talking about before, this steady state vector is really just going to be the eigenvector v of m with eigenvalue 1. And so what this PageRank vector is going to tell you is, loosely speaking, it's going to tell you like what the most influential or important page is going to be. So looking at the previous example, like what's the most important page? The most important page, intuitively, you might think is going to be the page that is linked to the most. So if you look at this graph that we have, C is linked to more than any other page. Like we have 3 other web pages that link to it. And it doesn't link to any other page aside from A, like it only goes to one other place. So it seems like C should be the most important. Meanwhile, B should be the least important because there's only one arrow that ends up linking to it, or one web page. And so what the PageRank will tell you is it's going to end up showing you, like it's going to give each web page a prescribed value based off of importance, and it'll show you that we can confirm that C will be the most important, so it should show up first on a web search, and then B should show up the least, or it should show up last in the web search. And I say, like in real life, the Google matrix again has like zillions of rows, whereas the example we're looking at only has 4. So you would have to require like a lot of programming to work for like a zillion by zillion row matrix. Obviously, I don't even know if zillion's a real number. I should say like trillion or something like that. So I'll go through this one really quick because we don't have that much time. Maybe I'll touch on it on Monday a little bit. So we considered the following internet. It wants you to find the PageRank vector for this internet with damping factor P is equal to 0.15. So it wants you to determine what web page is the most important and what web page is the least important. So the initial matrix we had, A, was equal to 0, 0, 1, 1/2, 1 over 3, 0, 0, 0, 1 over 3, 1/2, 0, 1/2, and then 1 over 3, 1/2, 0, 0. And so we don't have any columns with 0, or we don't have any 0 columns. So we have A is equal to A prime. That doesn't change. And we're going to let P be equal to 0.15 as the statement says in the beginning. And so we end up having in this case that M is equal to 1 minus 0.15. So this is the Google matrix multiplied by A. Oh, I should just obviously copy it and not just take the whole thing. And then this is going to be minus 0.5 multiplied by B. B in this case is going to be, again, this is a completely random matrix. We have 4 web pages. So B is just going to be 1/4 multiplied by the 4x4 matrix consisting of just 1. So it's going to be 1/4, 1/4, 1/4, 1/4. And then you just do this over and over again. It's probably smarter to just write 1/4 outside of the matrix and then just have a bunch of ones inside of it. So this is the Google matrix from the previous slide. I'm just using this definition here. Okay, and so in terms of decimals, what does this matrix end up looking like? We end up having that M is equal to the following.
Minus 0.5 Google matrix.
Oh, it should be point. Oh, it should be plus. It should be.
It's plus.
Oh, it should be plus.
Right.
Yeah, it should be plus.
And then 1.5. This P is 1.5.
Oh, yeah, that's right. Yeah. So I'm rushing a little bit. Okay. And so what this ends up being equal to is the following. I don't know if I'm going to have enough time to cover this. And this will be 0.3208. I'm going to do a little bit of copying and pasting to make this go faster. You end up getting the following matrix. I feel like I probably should have just wrote this out before class started. Yeah, this whole column will be 0.25, 0.25, 0.25, 0.4625, and then you have a bunch of 0.4625s. Okay, so you take this matrix and then to find the steady state or the page rank vector, all you do is you just find the eigenvalue, or you find the eigenvector of this matrix corresponding to lambda is equal to 1. And so in practice, what you'll do is you'll put this into some sort of calculator. But one thing you need to take note of, like if you do this on the homework assignment, it'll spit out an eigenvector that looks like this. So the eigenvector of lambda is equal to 1. It'll spit out something of the form of like 0.878, 0.702, 1.452, and then 1. So this isn't a Markov vector. Like you want to make sure that all these terms end up summing to 1. So you need to normalize. So you add up all of these terms, and then you just divide by whatever that sum ends up being. So you end up dividing by like the sum of 0. Sorry, I'm like pretty much done. I just need to write this out because this will be relevant for the homework assignment. So I want you to write it out as a Markov vector. So if you take whatever vector it gives you on like Wolfram or whatever program you use, you divide by the sum of the entries. And so that will give you a Markov vector. So the Markov vector ends up being 0.2192, 0.1752, 0.3558, and then 0.2498. And so in summary, the most important web page is C, web page C, as we predicted, and then the least important is B, as we predicted. Yeah, go ahead.
Why do you not divide by the square root?
We just want to make sure that the sum, I used the word normalize. I shouldn't have used the word normalize. Like we're just wanting to make sure the sum of these entries go to 1. So you just see what these add up to, and then if you divide by that, you end up just getting a vector that'll sum to 1. Yeah, so I kind of rushed at the end. Maybe in class on Monday, I'll give like a more total summary of what we just did. But yeah.